I'm getting ready to show you an animation, and there's some things I want you to pay attention to. First of all, our goal. Our goal here is to find the slope of the tangent line here at 1. What you see in blue is a secant line that's connected from x equals 1 to x equals 2. And that's not quite the slope that we want. The tangent line slope would be underneath this curve right here and would be a little flatter than that. So as I start this animation, you're going to see that h is going to drop in value. What that means is these two dots are going to come closer and closer together on the curve. And what we're going to do is we're going to make the average rate of change become the instantaneous rate of change, or the derivative, or the slope of the tangent line at a point. So I want you to watch this and pay attention to those. So you can see our 2 points are getting a little closer together. And our blue line is becoming closer to the value of the tangent line, or the slope of the tangent line. And what's happening to h over here is it's getting smaller. And what's going to happen is, look, it's starting to even get a lot better now. That blue line is becoming what we want, our tangent line slope. But what's necessary is that h must become very, very small. And so we can do that with a limit. So let's just finalize, yeah. So that looked pretty good there. So you can watch that again if you want to. So let's get some notation out of the way. We are finding derivatives, and which is also called instantaneous rate of change. I want to remind you about some notation that we've used. F prime of x, that's how we read that, f prime of x. That's our notation for our derivative. We also have another notation that we've used, and that's called dy dx. So let's go look at a formal definition and then see an example. So this is a formal definition for if we have a function and we want to find the derivative, it's this limiting process. And hey, we've done that before. We just didn't call it the derivative. It was a lot of practice with algebra, but we did it several times. So we are going to do the limit as h approaches 0 of our difference quotient, or our average rate of change. And if this limit exists, that's going to be our derivative. And what that derivative can be used for is to calculate exactly the slope of a graph at a specific point. And this process of finding the derivative is called differentiation. So let's go take a look at an example of that. So I've got a function 5x cubed, and I want f prime of 2. Now what does this mean, f prime of 2? This means the slope at the point x equals 2. So what we have to do first is we have to find f prime of x, and then we'll plug in 2 for x to calculate the slope. Then we'll go take a look on our calculator and see how we did. So let's first of all find our derivative, the limit as h approaches 0 of f of x plus h minus f of x all over h. That is our derivative formula, the definition of the derivative. So let's plug it in. So what is f of x plus h? Well, that means we're going to take x plus h and we're going to plug it in for x. So that's 5 times x plus h cubed. And then minus f of x, well, which is right there, f of x is 5x cubed. And this is all over h. See, we've done this before. This won't be too bad. We're going to do a little bit of algebra, and we're going to have to expand this x plus h cubed out, but if we remember the binomial expansion, it won't be too bad. But some of you can just go ahead and write x plus h times x plus h times x plus h and bust out your algebra. Let's go ahead and look at it. So I've got the limit as h approaches 0 of 5 times. Now x plus h cubed is x cubed plus 3x squared h plus 3x h squared plus h cubed. Whew. And then minus 5x cubed, and this is all over h. Okay, what do we need to do next? Well, we need to distribute this 5 all the way through here, and then we'll clean it up and see if anything cancels. So I've got the limit as h approaches 0 of 5x cubed plus 15x squared h plus 15x h squared plus 5h cubed minus 5x cubed, and that is all over h. Okay, well, what happened? Let's see. Let's clean up some things here. Looks like if I collect like terms, my 5x cubed in the front will cancel with this 5x cubed at the end. And also, I've got a common factor of h in the top. So let's take a look and see if I can get that to cancel. So I'll factor an h out. Make sure I get that right. 15x squared h. Looks good to me. All over h. And now we cancel our h's. And this, what we have left is we've computed our limit if we plug in 0 for h. So if we plug in 0 for h, it's going to cancel this term, and it's going to cancel this term, and we have our derivative. 15x squared is f prime of x. And what is that? That is how you find the slope of the graph anywhere you'd like. So let's go back and look and see where we wanted the slope. We wanted f prime at 2. So we are going to plug in 2 into that equation. So f prime at 2 is going to be 15 times 2 squared, which is 15, extend my page just a little bit more, which is 15 times 4, which is 60. Now that's a pretty steep slope. That is almost going like straight up. Let's go circle the answer and then look at it on our calculator and see if we agree with that. So I've got 5x cubed here, and let's graph it. Now we know our cube root function out here at 2. That thing is pretty steep up there. That thing is heading straight up almost. On your calculator, if you hit second trace and you go down to number 6, look at that, dy over dx. That is your notation for derivative. And so you can ask your calculator for dy dx at a specific value. And so I want it at x equals 2. Now my calculator is going to do some estimations here. It's not actually any better. As a matter of fact, it's a little worse than us. What we found was the exact value of the derivative. This is going to round a little bit, but you can see that at that point at 2, that graph is going up 60 over 1 at that specific point. That's a pretty steep slope. Now I want to go back before I end this, and because tomorrow in class I'm going to want you to look for some patterns. I'm going to come back here. There is a way to look at a function, if it's a polynomial form, to get to the derivative, and I really want you to be watching this tomorrow in class. We started with f of x, and f of x was 5x cubed. Now f prime of x worked out to be 15x squared. You've also done some average rates of change, and even some kids in class were saying, wait a minute, can I skip some of this algebra and just do this and this? I want you to be looking for that tomorrow, because we definitely want to find some shortcuts if we can. So see if you can find some patterns tomorrow in class, and I will see you guys then.